You can get more information or more useful tools for your research. So before we start, it would be nice if you can introduce yourself and say in which year of PhD are you working now, and in which kind of topic are you moving? Okay.
My name is Deepak. I'm second year PhD student. I work at the REHIB lab of Perugia University, and I work on two topics: high temperature alloy corrosions and hydrates.
Sorry?
We are focusing on the old length of the desk. So if you are out of the desk, then we don't see you. Now I see you and in all the desk.
Here, right?
Up to, yes. So the blackboard included.
Okay. So, sorry, topics?
High temperature corrosion of alloys, like around 800 degrees Celsius to 1000 in different environments, like corrosive carbon dioxide environments or others. And then the other topic is hydrates with CO2 injection and temperature and pressure variations.
Okay.
So those are the two topics. Mostly I deal with fluids,
Okay.
fluid transportation. And in terms of corrosion, it's mostly oxygen transport between the oxide layers and their propagation.
Okay. We are saying
Exactly.
like slightly topics to see what is the audience, so we can.
So my name is Claudia Fabiani. I'm a PhD student here. I'm about to defend my thesis, and the topic of my thesis was the characterization and the use of dynamic material properties in building applications. So we use them for affecting the indoor environment of a building and also the environment of the whole city. And we analyzed how to do that and what was the performance of the local microclimate by doing this.
So it's basically you did experiments
Both experiments and numerical
simulations
simulations.
for the
Yes. For the local indoor environment and the
also
local
numerical
environment of
environment.
the urban, yes. So the canopy, let's say.
I am Benedetta Piocchi and I'm a PhD student. This is my second year, and my topic is microclimate monitoring and modeling, and moreover I will focus on the relationships between the indoor and outdoor thermal comfort and the microclimate condition.
Hi, I'm Ilaria Pigliautile. I'm in the third year of PhD, so it's the final year. And my focus is monitoring of the both urban environment and indoor, but focus on the human perspective. So for the outdoor, we're developing a small system where we want to collect data at pedestrian level, let's say. So I'm working with this kind of data to see how to correlate to human comfort and urban configuration. And from the indoor perspective, I focus on different parameters, not just environmental, but like coupling with physiological and psychological ones.
And you did also modeling, right? In your business?
Macroclimate modeling, yes.
Laura?
I am Laura. I'm a computer student from the University of Perugia, and I'm in my second year of my PhD, and my PhD topic is related to organization of concrete as a thermal energy storage material.
Okay.
And I'm working on high temperatures and thermal.
Sensible.
Yes.
Hi, I'm Matteo. I'm a PhD student here, and I deal mainly with building dynamic simulations and also with thermal storage, mainly the sensible thermal storage, and I'm very interested in this topic.
Hi, I'm Matteo Sampoli, and this is my first year of PhD. The topic of my PhD is the thermal modeling buildings, dynamic modeling.
Hello, I am Ioannis Kousis. This is my first, actually month of my PhD. So
Lucky you.
the topic the title of my PhD is Cool Pavements for Mitigating Blue-back Heat Island. And for the moment I'm doing some literature review and most focused on phase change materials or thermochromic materials.
Okay.
My name is Fabiana, and it's also my first month here. And now I'm starting to read about PCM, to do paper
For buildings or?
for buildings.
Mhm.
And also starting to study about LCA, do some specific studies about smart buildings.
Okay.
I'm Costanza. I'm a PhD student here. This is my first year. My thesis was about railway noise, and now I'm going to study a CFD model for a double skin facade.
Double skin facade?
Yeah.
Okay.
Hi, I'm Valentina. This is my first year of PhD, and my thesis, the topic of my thesis is the thermal and acoustic characterization of a new material for the building application, and also some modeling, some kind of something. The modeling.
Hi, I'm Marta. This is my first year of PhD, and at the moment I'm studying cool roofs and reflective materials and properties.
Okay, so most of you are working in the, let's say, thermal field, buildings or storage, different temperatures. So I think the course will be interesting because they can give you tools that you can use in your PhD. For the ones that you are finishing, you can use it in the postdoc, or maybe you know already. For the ones who are studying, I think it's a very good time to get this knowledge. It's usually people do modeling in the PhD because it's an easy way to publish, or a straightforward way to publish. But if you can do it in the perspective, you will get better results and a better PhD at the end. So we will discuss later on. We have just 10 slides now. Then I will start with equations. But those 10 slides are very important just to keep in mind why are we doing all this. Okay?
May I introduce you?
I say some words. I'm Alvaro. I'm working in Yale University, also collaborating a lot with Ana Laura here. I did my PhD about double skin facades with PCM, but it was ages ago, so now don't ask me about that. And I've been dealing mainly with numerical problems in the lab in which I'm working. Okay. About the length of the course, I have divided this in 5 sessions because I know when we will start with equations, it will get tough, and I don't want you to get bored. So it's 5 sessions, 2 hours. Let's see how it goes from that. I will be here until Thursday afternoon. So if in any hour outside the course, do you want to ask me, okay, I have this problem or I have this another, how do you approach this heat transfer problem or whatever, we can discuss. So I'll be here around. Okay? So I wanted to title this course as Development of Numerical Tools and Coupling with Optimization Algorithm. This is the main tool that you will get out of this course. You will know how to develop a model, how to program it, and how to couple the model you can create with an optimization algorithm. Everything with free software, okay? Because I don't like to pay for something I can do by myself, okay? So, as I said, there will be 5 sessions. The first will be the introduction to numerical modeling, and then also the platforms of the software that we are going to use. Also today we will start with steady state problems. Then tomorrow we will probably end up with a steady state problem and go to transient. I will give some topics about the optimization using numerical tools, and at the end I will explain how to couple, or I will explain one way to couple the numerical tools that you will be able to develop against an optimization tool, and why this is so powerful. Okay. I also say some words about the REHIB project, which is the project in which I am contracted now, and I'm working together with Perugia University and University of Lleida, and in which we are actually coupling numerical tools and optimization algorithms. Okay, so that will be an example. It will be very boring if I am the only one that speaks for the 2 hours. So if you have any questions, comments, doubts, just you're free to do it. It is very important that in the meanwhile, maybe not today, but tomorrow or the day after tomorrow, while we are developing the different algorithms, you think in possible applications that all these tools can help you in your research. Okay, and then when you think, okay, this can be used, I can use this for that project, or I can use this for that problem that I have, then we can discuss together which is the best way to approach the problem you're having. Okay. So, first question I want to ask is why? Why we need numerical tools? Why are we here, and why are people doing numerical tools? And this is something you must ask yourself before doing anything. Before typing any word of code, before downloading any software, you have to ask yourself, why do you need in your research to develop a numerical tool? Because it will take you a while to develop. Maybe it's already in the literature. Why do you need to develop a numerical tool if it's already there? Which sort of problems is the numerical tool going to help you to figure out? So before doing any step, just think yourself why. People always think twice before buying any equipment for the lab in the experiments. So you have to justify to your PhD supervisor, you have to justify to anyone who's paying, why do you need this sample, why do you need this equipment, why do you need whatever, sensor. But because this is free, sometimes say, okay, I will try. But it is not free, it will take you some time to do it. So unless you are sure why you need the numerical model, do other things. We will figure out why. Maybe in your research we can discuss how the modeling can help you. But before this, a reason, an important reason, it's better you do not start modeling. Okay? Usually people do modeling because of that, because they create nice pictures. Presentations are fancy, papers look great, but all those pictures they're not useful. I mean, if I am analyzing the performance of a centrifugal fan or of a turbine or whatever, I will look for numbers. I will look for drag coefficients, I will look for impeller mean velocity, I will look for pressures, but I will not look to that map. I mean, who cares if one node is yellow or greenery or... Okay, it's very nice, but it will give you something scientifically. Can you conclude something out of these pictures? It's sometimes it's very difficult to get a real picture of what is going on with just those colorful pictures. Okay, so okay, they're okay in the conferences, in your PhD defense, it will look great, but numerical tools are useful for other things, just like measuring. Okay, so real reasons. First is that cost. So you are not able always to do all the experiments you want, and or experiments are not possible to be done. Like if I want to do a test in a rocket going to a space before I send the satellite or whatever. I need to do numerical modeling because I just have one shot. So I cannot do experimentally testing if it works or not works. If I am, for example, I don't know, studying flow in natural convection regime, experimental works are very difficult here, because if I need to put sensors inside the fluid with what is moving, the sensor will affect the flow and it will affect the motion. So it is difficult to measure natural convection effects without disturbing the physics that are behind. If I want to measure pressure at different points of a turbine, how do you do that? Inside, between impellers, between the blades? How do you do that? You cannot put sensors inside. So then numerical are very helpful for that. Okay? So first is experiments. You cannot always pay or design an experiment. Then numerical modeling are the only way or one way to do it. Second is, well, why we use them is because, you know, analytical methods are used to obtain exact mathematical solutions, but the differential equations that they are behind physical problems, they are not always integrable. So that's why we need numerical tools to have approximations of the solution, like very good approximations of the solution, but that's it. They are not exact solutions. They are approximations. How many of you are engineers? Most of you, right? So if you are engineers, be smart on that. I mean, you cannot achieve the exact solution, but what? If I am analyzing, for example, what is the temperature of the room because of the windows, if the numerical model gives me 23.6, it's okay. I don't care if it's 23.61. We'll get the same HVAC consumption. Okay? One big issue that numerical tools provides, that experiments is very difficult that can provide, is that variables or parameters inside a design can be optimized. I think it's almost impossible to optimize a design variable doing experiments. Like, for example, imagine we have only just one window, okay? And I want to have heating and cooling of this room. The window, the bigger it is, it's better for solar radiation going inside, but it's worse for heat losses. In summer, it's the other way around. The bigger it is, we have gains from the outside. So there will be an optimum size and shape of the window. How do we know it? How do we know it? It's very difficult to get experimentally which is the best shape to minimize consumption of heating and cooling during the whole year, here in this room, for example. One thing we can do is we develop a numerical tool of simulating the thermal performance of this room, and then we got, let's say, variable A, which can be height, and variable B, which can be width of the window. Then we can optimize that, variables A and B. The optimizer will ask to the numerical model, okay, try A equal to 5, B equal to 1. Okay, that is the consumption for the year HVAC system. Okay, now try 4 and 1. That is the main. And by asking and solving, you will get the minimum. At the end, you will find out, okay, the best design of A and B is 2.74 per 3.12, for example. In this way, you can optimize something. In any research you are doing, if you want to optimize PCM melting temperature, because it's something I use, but any you want, you can optimize. If you are doing experimental, the most you can do is parametric analysis, but not optimization. Okay? Another thing you can do is to control. Let's see, we have a design of the window, and I want to know which schedule minimizes HVAC control, which openings of the window minimizes HVAC consumption in the room. It's the same. I create the numerical tool, and then the optimizer says, okay, if you open at 1 and close at 2, what happens? And you can ask, and this is a control strategy. You can play, now for example, we are developing forecasting models in which for buildings, the building knows the forecasting of weather in terms of temperature and solar, the forecasting of grid, electricity price, and then you control the schedule of your whole building based on forecasting. To do that, you need numerical models. You cannot do it by experiments. Okay? Any question? No? Okay. So, as I said, before we start doing any equation or anything in the blackboard, you need to ask why do you need the numerical model? How are you going to use it? By solving this question properly, you will know which platform do you want to use. Like, you probably go to CFD. Probably you need to know to CFD. But maybe there is some particular case in which you don't need Navier-Stokes equations, or you don't need very detailed information, and you can go to simplified equations. It depends on what do you want to extract from the numerical model that will give you which platform do you want to use. Also, the second point, simplify the model as much as possible. Everything is 3D and transient. Everything in life is 3D and transient. But if you can assume that in the problem that you are working on, there is one dimension in which there are no gradients, or almost no gradients, there is no difference in one axis, then you can go to 2D. If there is asymmetries, if there is something that you can work with and assume that reduces the amount of nodes that you have in your domain, or the complexity of your system, then it's better for you. Like, I model PCM. I really try to avoid to simulate natural convection, because it's a pain in the ass. If you know the equations probably, natural convection, the fluid depends on density, and there is a motion over there. So if I am simulating a phase change material, part solid, part liquid, the liquid part will have movement. If the problem that I am simulating, it's in narrow cavities, or there are something blocking the movement or limiting the movement of PCM, I assume PCM doesn't move, because it costs me 20-30 times more computational effort to add this physics, natural convection. Okay, what is the effect of natural convection? It increases thermal conductivity. I mean, it increases diffusivity of heat, right? What if, in the literature there are plenty of papers out of that. What if I increase the thermal conductivity based on Rayleigh number, and I don't need to apply motion, I don't need to apply Navier-Stokes equation? That will save me a lot of time. And that's basically people that they are simulating PCM without using CFD are neglecting natural convection, or they are assuming an effective thermal conductivity to avoid natural convection simulation. You can ask why people don't go directly to CFD. It's more exact, right? But you are limited in CFD. In CFD, you cannot model a building. In CFD, you cannot model, I don't know, solar collector. It will give you only steady state problems with solar collectors. But if you want to model 1 year of performance of whatever, you cannot go and do CFD. It will take ages to converge. So you need to find the balance between accuracy and resources, computational resources that you are using. Of course, everything is 3D and transient, and everything can be modeled in console. but not everything will converge in CFD, sorry, not console. But not everything will converge in a reasonable time in CFD. Reasonable time, I mean months, for example. If you need to model something and optimize, let's say the optimization say, try these variables. Okay, wait 2 months for that. I will give you the results after 2 months. Okay, try those two. Okay, now try two other months to wait for the results. And like this, 2,000 times. Your PhD will take so much, more than 3 or 4 years, right? So you need to figure out if you want to use modeling, why. If it's something very precise that you need to go to CFD, okay, go to CFD, try to get a cluster or something, pay license, and that's it. But if you can assume and simplify your problem, always keeping in mind that all the assumptions are valid, and you are in an acceptable level of deviation, then go simple. That's my recommendation. From all the papers I have in the simulation topic, I have only one in CFD. In only one, I just used CFD. In all the others, I use simple tools. The ones that I will show you today, this week, how to do it. Okay? Okay, so that was, that was again the message. Once you figure out why you need the modeling, then you will be able to answer which platform do you use. If you are, let's say, simulating the whole building, you can create by your own, but it will take ages. You can go free license and G+. It works very good. It works okay. It has a plugin to connect directly with the optimizer that we are going to use, Genopt. The plugin is named G+. And it's, I mean, we are finding easy to publish using G+. It's because the model was developed, or the building model was developed by the Department of Energy. They have validated against experiments, so it's, if you are simulating the whole building, that's a good tool. If you are saying, no, I don't want to go simple, I need to know very precise which is the motion here, or what is the heat transfer coefficient here or there, I need to go to CFD, and you need license for that. In ANSYS Fluent or Console, you need license. There is one which is free, which is OpenFOAM. I don't know if you have heard about it, but it's not as user-friendly as those ones. Okay, so ANSYS and Console, they know how to get you to pay. If you use them, then you will not like OpenFOAM, because it's like coding in a CFD environment. Then you have MATLAB, which most of you know, MATLAB. You have to pay for MATLAB. Here in university, probably you have the license, right? But after your PhD, if you want to do in your company or in whatever, do you want to use the tools that you have been developing in MATLAB, or the knowledge that you gain in MATLAB, then you need to pay for that. Hey. And that's before we start, that's another thing that I want to pop up, is that the models that we are going to develop here, they can be used for doing research, but they also can be used for doing any engineering task. So it's not only about writing papers here. Like postdocs that we have from our group, they are working now in companies, and they are using this kind of tools to optimize designs inside the company. Like, I don't know how, if you know programming or not. In Spain, in engineering classes, we have programming classes in the first course. So when we finalize the undergraduate student studies, you don't remember like programming, so you need to refresh. I don't know if it's the same here in Italy, but I think it's very important that you are not scared about programming. It's a very good tool, and it will help you in any, not only in academic, but in industrial or any other job that you can have. It will help you a lot because you will be able to program PLCs, you will be able to optimize designs, optimize controls, and that's a skill that is not very common. And you can, it is like an extra value that you can provide to your CV. Okay. Finally, we have transits. Also, you have to pay for that. It's this is in case you want to simulate a system. Like, imagine you are simulating a solar field with a seasonal storage tank coupled to a district heating, right? The good thing of transits is that the models, they are already there. So you have a model, a box, black box of a solar field. You can control temperatures and so on, but there is already a model developed there. There is a model for a seasonal storage unit, for example. It's a huge water tank with a certification and so on. You have a modeling of the heat exchangers of the district heating or cooling. You have models of buildings. So this is very nice if your problem is in a system level, not in a component level. Okay. Also, you can couple transits with optimization tools, but you need to pay for that. I think people are using now Modelica for also. It's also system modeling. Okay. But what about free license software? So we are going to use C++ or C, and I will give you these slides. Maybe I can send to you, and then you share it with them. Sure. You can download it for free. The two software that we need for the course. Maybe not today, but tomorrow, if you can come with laptops or something like that, it will be nice, because then, maybe not tomorrow, but if we have free time, I will let you play with the softwares, okay? And so this C++, this is a C compiler. You can use whatever you like. Yes? No, it's okay, it's okay. We are going to finish with this, so I will start. You can use any C compiler that you can find for free. And then the optimization software that we are using is Genopt. And yeah, we are using because it's free and it has good environment, easy coupling with any software. Basically, what this software does is reads one TXT file and writes another TXT file. So it writes, try this to the numerical tool. The numerical tool writes the output in one TXT. I read the TXT. Okay, this is the output. Okay, this result, move this direction. Try this, and it's a program that is trying to optimize input and output. Basically, I'm using two different algorithms to, let's say, this search is not random. There is a smart search on that. So depending on the result, I will advise you to go one way or another. So there are different methods. I will explain you probably Thursday or Wednesday. But this is basically this tool, Genopt. Okay. So I already said that because we are not able to analytically determine or solve the problem, what I will try to do is to divide my domain in small pieces, right? And then what I know, or I assume that between the two pieces, the derivatives that are in the equations that are behind are linear. Okay, so the main concept of modeling is that if I have one thermal distribution, that it will be something like that. I'm not able to put the equations. I don't know. I cannot write the dependence of x and y, but what I can compute is different points of that. And between the two lines, I am assuming that there is a linear dependence. So I don't know. So I have this, I have this, I have this, I have this. This is an approximation, right? If I am asking just, okay, x equal to this, I will have two different results. The numerical and the analytical, if I could have it. But we need to live with that. If you need more accuracy, one thing you can do is to put more nodes, more mesh, right? Then the deviations will be reduced. I will say it later on, but sometimes adding more nodes is not a good solution because you can get convergence problems. But what this means is that if I want to simulate, I don't know, a car or whatever, I can divide the domain in different cells. The smaller the cells, the better results you will have. But the more computational effort you will have to carry out. Okay? Questions? No? Okay, so I think that was the presentation. So you know how can I switch? Okay. No. Any comment before we start with the, let's say, equations and boring part of the course? Even more boring than that. No questions? No comments? Okay. Want to drink something? Okay. So this I give in master courses. It takes a while to do everything, but I will try to sum up and do the most important part. So first thing you need to ask, so I divide when you are facing a problem, a steady state problem, that means that the physics that are behind your problem doesn't change with time, right? They are constant. Your solution will be, in the case of heat transfer, usually it's a map of temperature. That is the solution that you want to reach. Because with this map of temperature, you can estimate, I don't know, if you are designing a fin in a chip or in a processor, you know that there's heat being generated in the processor, and you need to you want to design a fin to dissipate all this heat, right? What you need is mainly the temperature distribution inside the fin, so you can compute it in each area of the fin, how much energy are you dissipating to the air, right? So this is map of temperature. In the steady state and in the transient problems, the solution will be evolution, the evolution of the map of temperature. Like in a dynamic system, like a building, if you are simulating the performance of the building, you are simulating how the temperature, for example, inside the room changes all over the day, all over the hour, all over the year. But it's a dynamic process. It's the evolution of this parameter, in this case temperature, in what is interesting. Okay? In case of a storage, if any of you are working in a storage, you need always have to go to transient, because you need to charge and discharge the storage. And you need to know the response of your system when charging, when storing, and when discharging. Okay? But before we go to the transient, I will start with the steady state, because the questions are a little bit easier or simpler. So I divide the process of doing a steady state problem into 4 parts. First part is doing assumptions or hypotheses. 2, as many as you can, always being realistic. I told you before, everything is 3D, everything is transient. I know that. But forget about going to 3D. And do transient if your outcome from the numerical model is the evolution of temperature. If you want to get a picture, don't go transient. So what reduces the most the computational time is to decide if it's steady or transient. Second, how many dimensions do you have? It's 3D, 2D, this is 2D axisymmetric, 1D, try to avoid 3D as much as you can. I know that sometimes it's difficult and you need to go to 3D, okay. But if you can, what you are exploring, try to convert it into a case study or in a numerical experiment that is not 3D. It's like when you are designing an experiment in the lab and you want to, I don't know, measure something specifically, you try to go the simpler you can, because you want to capture one phenomenon, right? So it's the same. If you want to explore, I don't know, how solar radiation affects one wall, then try to minimize the effect of windows, try to minimize the effect of other reflections. Think yourself if the angle of the solar radiation is very important. Ask yourself if how complex do you want to have the numerical model. Usually building walls are usually 1D problems. Energy Plus uses 1D models for each part of a building envelope, and it works. Like if I want to model the floor, I can use 1D, and some of you can say, yes, but in some hours, sunlight is facing just this area and not that area. Okay, you're right. Is this having a high influence? Ask yourself, I don't know. But what are you exploring? Surface temperature of the floor, because you have, I don't know, a pavement or whatever, or room temperature. Is room temperature very sensitive if the sun is just in this region or in another region? Can I assume 1D, and if the solar radiation is just facing half of the room, just compute half solar radiation? Is this assumable or not? Try to do tricks on that. And try to be engineering in this sense. So if I am adding complexity, it's because it deserves. Otherwise, keep the complexity for CFE. Okay? So Energy Plus uses 1D for floors, 1D for all the other walls and so on. And what it does is what I was saying. if hours in which the sunlight is facing half of the area, if it comes, I don't know, 600 watt square meter, it computes 300 for the whole surface. And that's it. I know that maybe the floor there will be warmer than here, but I will experience that in a comfort level. If yes, go to 2D or 3D. If not, try to reduce. Okay? So this is very, very important, because you will notice that 1D problems are solved like this, and this is very, very important when you are optimizing or both design and control. So this is not, at the end, if you want this course for the full skills, which means coupling, modeling, and optimizing, you need a light numerical model. That's because you will run thousands of simulations before you get an optimum. And if each simulation takes you 1 hour, people doing CFD will say, 1 hour, that's nothing. Yeah, okay, but 1,000 hours, it's something. So, try to go simple as much as you can. Then, symmetry is very important to reduce the domain. Like, if you know that there's something that has the same boundaries, you know, you can do, you can apply symmetry. Like, for example, if I am doing a pipe, which has, I don't know, insulation here and here. There is water going in with a temperature and a velocity, and I want to know at which temperature goes out. I will do axisymmetric here, so I will discretize domain in different nodes. But this part I can neglect, right? Because this surface, this point, will behave the same as this point, right? In a pipe, this point will behave as similar as this one. So I don't need to, that's the same node as this one. Okay? So in this way, my domain is this one, and each of the nodes that I'm going to divide, I know that the geometry, it has like a cylinder. Okay? If I am, if I have, let's say, a cube, a square, 90 degrees, and I put it in the air, 30 degrees, 30 degrees, 30 degrees, and 30 degrees. I want to determine how much time do I need before the central node, the central part, gets to 30 degrees. That's a transient, right? I need an evolution. Something is charged. Maybe the sensible storage unit that Laura is working on is, imagine it's concrete, and instead of 900, it's, 90, it's 900. We have a stored solar energy in that concrete box. And we leave it outside. Okay, we have the same boundaries, so I cannot model that analytically. I need to do that, like draw small nodes, and now I assume, or I can compute, for example, how this node evolves. This node evolves downward, because at the very beginning it was a 900, and it is touching something at 30 degrees, right? So it will start to dissipate heat outside. The temperature of this node will depend on this temperature, on this temperature, on this, on this, on this, and on the air temperature, right? Let me open the light. Okay. Now, what I was saying about symmetry is here we can apply symmetry. We can apply one axis here, it's the same this way and this way, and we can apply symmetry here. It's happening the same here and there. So at the end, my model, it will be something like that. 30 degrees, 30 degrees, all the nodes at 900, and adiabatic, and adiabatic. Why adiabatic? Because as this node is having the same temperature of this node, there will be no heat conduction between them. So this is adiabatic. This is computationally 25% cost as that one. And it solves the same. But try to reduce as much as you can. Symmetry is a very good tool to do it. Questions about that? No? Okay. Another thing that I think is important, physical properties, thermophysical properties in your simulations. I know that density, conductivity, viscosity, heat capacity, everything depends on temperature and pressure if it's a fluid. But is the change very significant? Like, if I am simulating a room, I always be between 15 degrees and 30 degrees, right? My thermal range is between 15 and 30. Do I need to apply thermophysical curves inside the model, or I can assume they are constant values? Because if I assume they are constant values, that makes convergence simpler. I know density depends on temperature, but what is the density variation between 15 and 30 degrees? Is very high, is significant? If yes, if for what you are studying, yes, I need to apply the density curve, then apply it. If not, if you don't care, if you can go constant, go constant. It's something you have simplified the model in some way. Okay? So, thermophysical properties. Also, ask yourself, usually it's the case, but you have to think if your the materials that you are using in the properties that you are playing with, they are isotropic, or if not, like if they change on direction or doesn't change on, they don't change in direction, you have to think about that when implementing your model. Okay? Questions about that? No? 1 hour, 0 comments, eh? We are in bad shape. Okay, then let's go to the second part. If you want to do a break for I don't know, cigarette or whatever, just let me know, okay? Okay, so second part is discretization of the domain. So now you have a geometry of whatever solid, whatever system, whatever component that you want to model because you want to improve it or you want to analyze it in any way. As an example, let's say I will draw a building wall of one component. Because of the wall, as the wall is in this direction, very long, I can assume that there is no heat transfer in the vertical direction. Usually in buildings there is no heat transfer in this way, but the main gradients are in the way from outside to the inside environment. As it is out, this is in, okay? And here we can have solar radiation, we can have a profile of temperature, whatever. Okay? And I want to know the response of the building because of that impulse. Okay? And imagine that inside I want to be at 24 degrees in comfort. I want to be in 24 in August. And the way to keep this 24, because it will get solar radiation and it will get temperature, is air conditioning. So I pay. So at the end, I will have heat flow going and leaving, right? Depending on the hour of the day. In sunny hours, this surface will get warm a lot, and it will be charged. All this heat will be dissipated inside, charging the different parts of the wall, and at night, all this heat will be released outside, right? So this is like a dynamic system. The wall temperature will be doing something like that. Imagine, it's not the case, but imagine we start everything at 24. Sun appears. It will start doing something like that. More sun. Sun is over. Like this. And now it will start to reduce. Probably at night it goes down to 24. This is 24. Right? This evolution is affecting me because at the end we have here a heat flow going inside my building. And that means money. Right? So let's see how we can start with this, or how we can discretize a wall, which is the simplest problem to solve. You know all the curves that I have been drawing here. I don't have any way to calculate them analytically. So I cannot know the thermal distribution of a concrete block if we have this sun and this temperature. What is the thermal distribution? I don't know. I need to do a numerical model to figure out and to calculate how much heat is going inside. Okay? So I cannot solve it because there's transients, there are things inside that blocks me to do it. So what I'm going to do is, okay, I will divide this solid into n parts, to different parts, and I will assume that the relation between each part is linear. Okay? So I will discretize the domain, so I will divide the domain in different nodes. So, for example, I will have y equal to 0, which is I means is you can use whatever you like. I'm using y always. Y equal to 0 at the node which is staying to compute the temperature of the surface. This is I equal to 1, 2, 3, and 4. Okay? You can use 20 nodes, 30 nodes, 100 nodes, 1,000 nodes, whatever you like. The more nodes you use, those curves that we were printing, that will be more accurate. Okay? By dividing the domain in different nodes, I am assuming that I have colors. Yes. All this area is at the same temperature. So what a node means is an area, isothermal area, for a heat transfer process. Heat transfer problem. If you do motion, the node will have a unique velocity, a unique direction of velocity, a unique pressure, unique temperature, unique density. So you are assuming that all this space is behaving as a single point. Okay? So the thinner you go, the better. Okay? I mean, I can do a numerical model just doing two nodes, one in, one out. But then that means that there is always linear. I mean, if I'm being so rude, like I equal to 0, I equal to 1, just two nodes, that means that all this area is at one temperature and all this other is another one, it's in another temperature. Which means that all the curves that I was printing before are always straight lines. Always straight lines. And that's not very accurate. Okay, because the wall will start to heat from the outer part when the sun is exposed, right? Then he will the first nodes will start to accumulate solar radiation and dissipate to the other nodes, right? So I need to have, I don't know, 20 nodes probably here, but depending on the thickness and the material. Okay. So now the concept is simple, right? I'm dividing the geometry. Any question on that? No, right? We cannot address the whole problem, so I will try to address small problems. And then by solving the different small problems, I will get to an approximation of the big one. Okay? Now, this is easy to draw, but we need to make it understandable for a computer. Okay? So we need to, I will give you an example on how to note everything in a way that at the end you can program it in a computer and the computer can know that, okay, you have this solid and you have 4 nodes and all these. Okay? So that's what all these equations are about. Are about how we give the geometry to the software. How can I code this into something that the model can understand? So imagine this is L, like the thickness of the wall, and this is the thickness of each node. Okay? So yes. The thickness of each node is equal to the L, to the thickness, divided by the number of nodes in which I want to divide the domain. N, in this case, is 4. N, in this case, is 4, but we have 5 different nodes. Right? 0, 1, 2, 3, and 4. 5. The first and the last node are half thick from the other two. Okay? I strongly recommend you to do this. Some people don't do it, and you can face convergence problems at the end. So, because what I want to compute, I mean, this node stands for the surface. The most interesting thing that this node will give, the most interesting information that this node will give is how the outer environment affects the surface. So if I have and divide it like this, then this node has a lot of mass and less influence in the surface than this one. Do you follow me? So, in the edges, always the nodes are half the thick or half the dimension of the other ones. Okay? So, imagine this node will have convection here, we'll have conduction going here, this node will have conduction and conduction, right? This also conduction and conduction, and the last one, convection and conduction. Okay? We'll face equations at the end. Energy balance will do it later on. But it is important that we define for the computer how thick is your node. And the way you can the computer calculate how thick is length. This is an input. I will say L equal to 0 meters. I will say this command to my model. And I will decide how many nodes do I want to use to discretize the wall. Use 50 nodes. Okay. Then 1 centimeter each. Each node is of 1 centimeter. Okay? It seems easy, right? It's easy. So you will see that it's easy. So there is no rocket science behind this. Now, for each node, let's say I will get this one, for example. Imagine, I will draw this I equal to 2, right? Here's adiabatic, there's no heat flux, there's no heat flux. Each node inside the wall will have a node in the west, we'll note it like W, and a node in the east. When I am solving node 1, 2, and 3, I really don't care about any other thing like what is the temperature of the node before and after. I don't care what happens outside my neighbors. And this is very important. And this is why we are able to solve. Because to solve the whole building wall, I'm just solving step by step the different nodes. And each node, the temperature of each node, they only depends on the temperature of the neighbors. Okay? So this is delta x, right? So this is delta x half and delta x half. Okay. Because in the case of, for example, node number 2, I will have to compute conduction from 2 to 3 and from 1 to 2, right? I will need to know the area, SE and SW. The area that contacts the node that I am calculating now, for example, number 2, with the east node and with the west node. In this case, imagine that the wall has a height of whatever, 3 meters, and a width of 10 meters. Area here and area here is the same, right? It's 30 meters. So SE are equal to SW are equal to height multiplied by width. Simple. We don't have to do anything else. Any question? Very simple, right? So the thing, what we are doing in this second step is preparing geometry to be able to be understood by the computer. That's it. Nothing else. Can I? Okay. So let's do it a little bit more interesting. Let's discretize the domain of a film. Imagine we have this fin, in which I know the temperature of the wall, and I know the temperature of the air, and the heat transfer coefficient with the air. How do you notice heat transfer coefficient? H or alpha? Here. H. So I know the heat transfer coefficient between the air surrounding the fin and the fin, okay? And I know that this pipe, maybe there's a fluid inside, or maybe it's generating heat because it's a wire or whatever. The boundary condition that I am imposing at the base of the fin, I know the temperature. It's, for example, 70 degrees. And I know that air temperature is 25 degrees. So I want to know the temperature profile all over the fin. And by knowing the temperature profile all over the fin, I will be able to know how much heat is dissipated from the fin to the air. Okay? Okay, let's do the same. I cannot analytically solve that, so what I'm going to do is to divide these into different nodes. This is delta R in radius, okay? This is half delta R, and this is half delta R. Okay? Because, as we said before, first and last, I mean the nodes at the boundaries are having half thickness. So in this way, the center can be drawn in the edge, in the boundary. Okay? So imagine this is RA, and this is RB. What else do we need? And this is the thickness. Okay? Now, those are inputs. I will say RA equal to 15, RB equal to 30, T air equal to 25, H air equal to 10 baht meter square Kelvin. Those are inputs. Everything here, T wall, 70 degrees. Now, solve the profile. Thickness, 2 millimeters, I don't know, or 1 centimeter. Okay? Those are inputs. Now, how we start and make the computer understand that we're having this discretization. First thing is that how much is delta R? Delta R will be RB minus RA divided by N. Right? Okay? Now I will be, as you can imagine, I will be, I'm dividing the domain in different nodes, and the computer, what it's going to do is, it will start with here, he will apply equations, get results. Go here, apply equations, get results. Go here, go here, go here, go here, and so on. I need something to make the computer understand where he is, and which equations does the computer has to apply. Because there will be different equations for this, and for that. There will be different equations to apply. Like this one, for example, has convection in the surface. This has less, sorry, I'm not very good at drawing. This has less area of convection than this one. Right? This area is higher than this one because it's a cylinder. So the higher the radius, the higher the surface. So I need something to make the computer understand where he is. Okay. I will note in the same way I will divide node P, node west, node east. I need to compute what is RP. RP is always RA, yes, plus I multiplied by the gradient in radius. Here I have y equal to 0, 1, 2, 3, 4, 5, 6, 7. N equal to 7. So, where am I? The radius from here to here, the difference is one full gradient, right? I mean, if this is one gradient, this is also one gradient, correct? I mean, if this distance is 1 centimeter, this distance is also 1 centimeter, right? So, we start here. For I equal to 0, what is the radius of my node? RA, yes? We're in the wall. If we start advancing, for I equal to 1, it's RA plus the gradient, right? If this is n, you can imagine that if for I equal to n, that will mean that we have RB minus RA divided by RA multiplied by RA, right? So this and this, this and this. RP equal to RB. Yes, correct. We are in RB. Okay, this is it seems silly, but it's the way to make the computer understand where you are in every moment. Now, because I will have to compute conduction between two nodes, I will have to compute the surface between two nodes. I mean, if I'm looking to this node, number 4, it will look like this. This is number 4, imagine. Number 4 will receive conduction from the west, will provide conduction to the east, and it will dissipate convection. For example, to calculate convection, I have heat transfer coefficient, right? And I can compute the area. I will do it later on. But to estimate the conduction between the two different nodes, between node 3 and node 4, that depends on the area between the two nodes, right? Because of Fourier. The higher the area, the more conduction you have, right? So, because it's in cylindrical coordinates, you have more area here than here. So you have to compute area here and here to calculate the conduction coming from the west and the conduction going to the east. For that reason, I will need to know for each node what is the radius until the west wall and until the east node of my node. R west for each node, except the first, is RP minus half the radiant gradient. RE, except for the last, is RP plus, correct? So now the computer, if I move in a loop from I equal to 0 to, you know what a loop is, right? So you start I equal to 0, it will execute I equal to 0, everything. Now I equal to 1, it will execute all the lines, 2, 3, 4, until I equal to n. Doesn't matter if n is 7,000 or 7. If it's 7, it goes 7 and it goes up. So now, if I enter the loop with 0, I know the position here. This doesn't exist because this has no node in the west, and can execute the east, which I need to compute the conduction from 0 to 1. Now, I execute I equal to 1. Okay, I know where am I? I know the radius connecting me to the previous node and the radius connecting me to the following node. Okay? Because the surface facing the west for conduction will be R west multiplied by 2p multiplied by thickness. That's why I need RW. In the same way, the surface that I need to calculate for this conduction, it's 2p RE multiplied by thickness of the thing. Yes? Now, each node has different surface for convection also. Because these nodes have more area in contact with air than the first ones. That's area of convection. That will depend on I. It will depend on the position. That's why it's very important that I give to the computer the information on where you are. Because depending on where you are having one geometry or another. Okay, that is 2 pi RE R. 2 because you have surface in the top and the bottom of the node. Okay? Any question? Now, volume, the same. For steady state problems, I don't care about volume. But for transient, I do need to care about volume. Because the more mass you have in a node, the more energy you can store in that node. Right? So, if I need to compute, that is so each node has its own volume. This has an exception, so this is like valid for from I equal to 1 to I equal to 6. So if I is equal to 0, the convection area is 2 pi RE minus RP. And the volume of 0 is PRE, sorry. Because the first node doesn't have any west node. And for I equal to n, the same but in the east. Clear? I'm just, it's very simple. I'm not doing anything new, but this is a good way to note everything in a way that the computer can understand at the end. Okay? Any question until here? We're going fast, which is okay. Maybe on Thursday we have holidays. I don't know. No question? Okay. Can I erase? Yes? Now, let's move. Now we have discretized the domain. We have divided the geometry into different nodes and note in a way that the computer can understand what we are doing. We are going to keep with the same example, but we move for the third, which is obtain set of algebraic equations. What we have done until now, you can do it no matter the physics you want to apply. So if you're doing acoustics, you probably need to discretize the domain anyway. If you're doing fluid flow, you need to discretize the domain. If you're doing, I don't know, yeah, also the same. Now I'm going to apply energy balance equation, conservation of energy. But the way we have discretized a solid is the same for any physics you will apply. Okay? Okay, so now let's move to I don't know why we are anyway. Okay, the course, the topic of the course is not heat transfer, but because I'm usually, that's why I teach this way, okay? This is the conservation of energy. Depending on the assumptions you have done before in the step 1, you can start neglecting things here or not. So this term, so imagine you have whatever solid with one heat flow going in, one heat flow going out, another heat flow going in. This term, this component of the equation stands for that. For I want to figure out what's happening in this domain, and outside the domain there's heat flows going in and going out. Okay. This term, it comes if some work is done inside the domain. Usually in heat transfer problems, there is no work. But this is an assumption you have to verify. That's 0. Now, that stands for the variation of energy inside your domain over time. Your node or your domain, in this case, can vary its energy in terms of kinetic energy, potential energy, or internal energy, right? Usually, we have this 0 and this 0. This not because your domain can change the level of energy that it's inside your domain by varying its temperature, for example, or by changing the phase from solid to liquid. So it has different internal energy and hence different enthalpy. You follow me? Yeah. And this, it means from mass flow going inside or outside the surface of the domain. So if here we have mass 1 with a temperature 1 going inside. Here we have a surface. This is surface 1. This is surface 2. This is a mass flow rate going outside with another temperature. This is another one going outside. Whatever. This integral stands for the sum, for the addition of all the different, like N3, T3. The mass and the energy that is associated because of mass transfer from the boundaries of your domain. Okay? So, in this case, we don't have any mass issue. right? That term usually is 0, this is 0, and that usually, you know, like MCP T in minus T out. You know this from your energy balance equations. This came from that. Velocity multiplied by density. A surface, you have mass flow rate, you have CP here in the enthalpy. Okay? But we will look for that maybe if we have time on Thursday. Now, in the case that we are doing, we don't have any exchange of mass in my fin, right? There is no mass going to the fin or moving outside the fin. So in this way, there is no ds, there is no surface of mass exchange. So that is 0. For that, everything is constant in temperatures. Like, wall temperature is always 70. Air temperature is always 25. Heat transfer coefficient is always 10. So this is a steady state problem. There is no evolution in time. That means that this derivative is 0. There is no accumulation because the nodes are in a picture. You want to do a picture and your solution will be a picture. There is no evolution. There is no change between one time step and another time step. So this is it. So we get to this equation. Nice. You know, a lot of integrals for nothing at the end. But it's important that you understand why we are assuming all this. So, now things are moving simpler because we have assumed that this is steady state, because it's 1D, because there is no work, because there is no mass difference between the air and the fin, because all the assumptions that we have made, that they are reasonable, all of them, then now the equations will be very simple. Now, which equations are we facing? I will start with node number 1. Or can I erase this? Yeah, right. Okay. For any node between 1 and 6, I will write the equations now. You can imagine that node 0 that doesn't need a equation, because what you want to solve is temperature in this case, and you know the temperature of node equal to 0, so you don't need to apply any equation. It's direct. T of node 0 is T wall. That's it. Now the physics of, or the equation of 7 maybe will be slightly different, because all the other nodes will have conduction from the west, conduction from the east to the east, and convection. But this one will, this node will have conduction to the east part. So it will be slightly different. But so let's say for 1 y to n minus 1. In that case, any of the nodes can be do a sketch like this. So we have do you agree with me? Each of the nodes between 1 and 6 have a conduction coming from the west, a conduction going to the east, and is dissipating convection. Right? Okay. How can I compute Q conduction west? Oh, Q west, I say. Now, this is minus thermal conductivity of the fin. The derivative in the space of R of the temperature. When we calculate, where do we calculate this derivative? In the boundary of the west. Multiply by the surface at the west that we have already computed in step number 2, right? This is more or less, and this is the approximation that we are going to face because we cannot solve this derivative. Minus k Tp minus Te divided by delta R multiplied by S. Sorry, west. Agree with me? It's a gradient, so I go forward minus backward. Tp minus T west. That's the gradient. That's the geometrical gradient. I compute this difference in the surface between the two nodes. And this is K, this is thermal conductivity. You use K for thermal conductivity? Okay, let's do any question? No, right? Simple. Fourier, second course of undergraduate. If you go east, it's the same. This derivative is approximately a gradient because we are going narrow in the number of nodes. Right? So this is minus K, T east minus Tp divided by delta R. Oopa. Because we have written in a way that the computer can calculate easily what is SW or SE for I equal to 1, I equal to 2, I equal to 3, then goes directly. Okay? So in case I is equal to 1, it will be like this. In case it's equal to 5, it will be like this. They're different values. They are stored in the computer, it's okay. Now, another thing that we are having related here is convection. H multiplied by Tp minus Tr multiply by area of convection, which depends on the node also. That will be 1 or 2 or whatever. Questions? No? Good. So, let's do, from the energy equation we got this, right? Because we are in a steady state, we have to, there's no accumulation of energy. So all the energy going inside the node has to be released by the node. Everything in, everything out. So what is in? Q west minus Q east minus Q convection is equal to 0. Okay, let's go here. Q west minus K, Tp minus T west. Now, minus Q east plus K T E minus Tp divided by delta R E minus H Tp minus T R. Okay, that's the equation I have to solve for each node. And remember that when each node, in the calculation of each node, I'm only worried about what happens to the neighbors. I don't care what happens outside the neighbors. So if I'm solving node number named P, I care about east and west. That's it. One important thing. One can ask me why I assume that those are the directions of the flow, of the heat flow. Now, because you know the numbers, you know 70. But imagine this is 10, or no, whatever. It might happen that you don't know the direction of the heat flow. In this case, we know, because I put the numbers here. And because this is 70 and this is 25, we assume that the heat flow will go this direction and towards the outside. But imagine we don't know that. We can write the equations in a similar way. It doesn't depend on those values. Just what you draw, keep it in the equation. Like, it doesn't matter if it goes this way or not. If you are wrong, it will get the other way. No problem. Okay? So I am assuming that the west was this way, positive. If it is the other way, then that value will become negative, and that value will become negative. There's no problem with that. The only problem that you have to respect is this definition. If in your equation says convection is negative, that's because the temperature of the node is higher than the temperature of the fluid surrounding your node. You cannot put this as you like. So you have to respect the direction that you have decided here. You have, okay, I think that temperature of the node will be higher than temperature of the air because it's leaving the convection. Because it's leaving, here is negative. I assume that, so I put it this way. Now, if it's the other way around, no worries. It will converge and it will give these negative values. But if you put a negative here, don't flip signs here. The same with convection. You can do whatever you like in the direction, the definitions. I always assume, I don't care about the problem. I always assume that flow is going from left to right and from down to up. Always. Then values become negative if they are negative. Okay? Good. So now we need to isolate Tp. So we are calculating the temperature of my node based on the temperature of the neighbors. So now, what is Tp? Tp is okay. I have been doing this so many times, that's why I hope it works. Okay, so this is the equation that solves me the temperature of the node P, depending on the temperature of the neighbor on the east and on the west, and on the air temperature. So we have like a constant for the west, we have a constant for the east, we have independent term, and here that is, right? Figure out that you don't have to compute this. The computer will compute for you. So now, you can imagine, both how boring. This is tough to write. You have to write it once. Once. The computer will do the calculations. And this is area. This is a geometrical parameter. AW, this term, is surface and gradient. Surface and gradient. Heat transfer coefficient is an input. Area, you have calculated. TR is an input. You can know it like this with a computer. So at the end, your equation is AW multiplied by TW plus it's not very complex. Okay? Any question until here? Now, you help me with, we have done from 1 to n minus 1 for the equation. This is for I from 1 to n minus 1. If I is equal to 0, the equation is direct. Finish. Right? Now, if I is equal to n, then we don't have this term. Right? We don't have this. So, I do it? Well, at the end we start here the same, right? It's equal to 0, that means the convection coming from the west minus the convection will be equal to 0. If we do all the terms, it will end up same way. You can do it if you want, but it's just the same process that we have done for the only thing is that the area of convection will be different. Okay. Actually, the area of convection for the node 7 is this area, plus the ring, this thickness. True? You compute it. It's 7. It's RP 2 pi RP square RW square plus 2 pi RP multiplied by thickness. I think I'm correct. Yes. Right? The area of convection will be that one, the one below, and the one surrounding. Okay? So we have these equations. Now it's 5 minutes to finish. Can we finish 10 minutes after? Or are you in a hurry? It's in this way you can understand how all these all ends. Okay? Now, from a complex problem that we don't know how to solve it, we could get simple algebraic equations for t equal to 0, the simplest one, the one at the top. From 1 to 6, the one here. And for the last one, this one. Okay? Now it's a matter of solving that. What problem are we facing now? Now, imagine I go to these equations, I equal to 1. Okay? AW, AE, VP, I know the numbers. For 1, 1, 1, 1, and 1. I have computed. I know the numbers. Now, for TP equal to 1, that is 1. The west node is 0. The east node is 2. Okay, I start T equal to 0, T wall, perfect. T equal 1. I try to apply this equation, but I don't know this. Right? So I cannot determine the value of T1 because I don't know value of T2. Okay, let's go to T2. If I move to T2, then I don't know T1 and I don't know T3. Remember, we are calculating the value of each node depending on the neighbors, but I don't know the neighbors. So, how we do that?
Create a dependence.
Sorry?
Just create a dependence based on T wall.
Yeah, but this dependence is the analytical solution. We are doing all this because we don't have an analytical solution. So now that's why this the numerical model came. And the strength of the numerical tool is that it is iterative. So I don't know, I'm calculating T1, but to calculate T1 I need T2, which I don't know. Okay, I will assume a map of temperature. I will assume a values of T0, T1, T2, T3 until Tn. I will assume. With this assumption, I will calculate the values based on my equations. And I will get a map. And I will ask the code. The assumptions that I made were correct or not? Or they are there's a high deviation between what I assume and what is after the equations. Oh, you're far from the solution. Okay, now, my new assumption is the solution that I got.
Is this the convergence?
Yes. Now, I draw the algorithm of solution. Can I erase this? Yes?
So this is in the initial value problem, no?
No. Well, I will keep that in mind.
In E plus, in energy plus, it's at the layer to 24 degrees.
And you have warm-up days.
Yeah.
Yes.
Okay, it's the same.
Yeah, but
something like.
But do you know where we start? Where do we start? This is at 70. This is at 25. What is the value of T2, T3, T4, T35? Imagine there is 70. We don't know, right? So there is a way to do it. So imagine now we start. Okay, and there is a solution. Go home. No, after all this boring stuff, there's something to do. So now I will write the structure of the algorithm that you need to use to solve this problem. First block of your code will be input parameters. Here you need to add geometry, physical properties, boundaries, and two values. One is n, the number of nodes that you want to use, and the other one is this delta, which is the error that you can accept. Now we will see where the error is. Okay? First thing that the computer will do is, with these parameters, he will calculation of coefficients. That means surfaces, AW, AE, BP, and so on. All the coefficients that we will need in the, for the equations. Keep in mind that all those are arrays, are vectors. They are not constants. That means that you have a surface for, that depends on y. That depends on y. Also depends on y, depends on y, and depends on y. Depending on the position in which you are inside the fin, you have different coefficients. So each of that is an array. It's a vector of values. Of n values. Correct? Okay. Now, we will start the calculation. Opa. First thing I'm going to do is all the nodes in my domain. I will assume, and I will use, this is how this is in English? Asterisk? Okay, similar to Spanish. All of them are T0. T0 can be whatever value you like. But the closer to the solution is, the less iterations you will move. We will see it at the end. So now, I don't know what is the thermal distribution of all these. So to calculate one, I don't know the value of two. But I will assume, for example, that everything is at 70, at T1. Everything is at 70. I know it's incorrect, but it's something, somewhere where we can start. Okay? So, imagine T0, it's 70. It can go 70, 25, 30, whatever value you like. The model will converge anyway to the solution. Now, with this assumption, I will start doing what this means Gauss-Seidel. And what's happened here? For I equal to 0, go to the equation. Okay, T0 is T1. For T1, what we have? We have AW1 multiplied by T0 plus A east 1 multiplied by T2 plus BP1 divided by right? That's the equation we have been working with. Now, T equal to, same. Right? Okay? So we are going to run from T0 to T7. T7, which is n. I will have the value of MS. Again, if I'm calculating T1, I don't know T2. Okay, but remember that we are using the asterisk. This is assumptions. I don't know if they are correct or not. All the temperatures that I'm using are assumptions. Here, no, this is not here. We don't need here because it's a UDP definition. Do we agree? Now, what we get? We compute T0, we compute T1, T2, T3, 4, 6, 7. Now we have a map of temperature which are solutions, and a map of temperature which are assumptions. I assumed that everything was at 70, but I went here and it gets T1 equal to 62. But I assume it was 70. Now I have two maps. Do you follow me? I have a map of solutions after passing to the equations which I wrote them, and a map of what I assume. Now I will ask. So down, but I cannot. So the question is the maximum deviation so the sorry. That is why I need to prepare slides. Now I ask myself, the maximum deviation between the values I have, for example, y, ty, and t asterisk y, and ty. 0, 1, 2, 3, 4. First, I assume it was 70 everything. And now the results are, okay, this is 63, 61, 48, 41, 26. The maximum deviation between those two, which are 44, it's below the maximum error I can afford? No. Maximum error, usually, it's 10 at the minus 6. So we have 44 of deviation. Something goes wrong here. Now, what I'm going to do, I will say, let's go direct today. The new iteration is the solution of the past. And with this value, I'll compute again. May I repeat? Because I didn't have any clue, I started with 70. And after passing through all the set of equations, I got a map of temperature. Now, what I assume and what I got is the same. No, it's not the same. So now, do the same process, but assuming the map that we have calculated. Now, this will be assumed. And I will get another iteration. Now, what I get? I got 61, 59, 47, 40, 25. What is the maximum deviation between those two? 2. Is acceptable? No, it's not acceptable. The maximum deviation is 10 at the minus 6. But, okay, so now do all the equations with this assumption and create until there is no difference between what you have assumed and what you have got. Then, that means that you have calculated everything with the proper assumptions. You have calculated T1 with a good assumption of T2 and with a good assumption of T0. That means this value is correct. Any question? Sure? So that's why it is iterative. The computer can do 1 million of iterations like this. So you need, this is impossible to, I will show you tomorrow. The first thing we will do is I will recreate a similar example with the computer. And I will teach you how you will translate the blackboard into the code. Okay? And then you will see that I will press the button and you will get the solution directly. So it seems now a lot of work, but it's of course nothing. Okay? But it's important that you understand the concept, because this concept you can apply for any physics. Now we have applied the physics for the temperature, but you can apply it for any. Acoustics, mechanical strength, fluids, whatever. We have assumed that each node depends just on the neighbors. We don't know the neighbors, we assume the neighbors. And we evolve this assumption until it converges, and it will converge. Okay? See you tomorrow then? Great, thank you.
Thanks.
Thank you.